Hello and welcome everyone to our 8th and final tutorial video. Today we are going to create defect directories for the defects that we have generated in our previous video, and we will try to run some simulation. So let's get started with that. So as you can remember, previously we have been working on this defect folder and we tried to create some defects of different types that includes like vacancies, interstitials, antisites, and also like some impurities like silicon and magnesium to our gallium nitride device materials. So this is the defect in a registry. So all these different types of oxidation states needs to be calculated. So for like this file we have like 7 different charge states. So we'll try to create 7 different folders and we'll do VASP calculation for each of these charge states. So we will repeat this whole process for all these different types of defects because after that then we will be able to generate our formation energy diagram. So let's get started with that. So let's start with our GitHub repository. Let's come to the step 10. So we'll go to this like this step 10 section and we'll copy paste this code. So what this first command, it actually creates the directories. So what it will do, that it will work on this file and will create all these different directories that are required, and also it will create a defect entry.json file. So this file actually refers that using this defect in file, when I am creating this directory, the summary is actually held in a file that is called defect entry file. So if you want to like know more about these commands, you can come to this PyDefects official website and you can see all these things from here. Okay, I am just copying pasting it. Let's go to the terminal. So you open the terminal from the defect section and run the code. So since this code will create a lot of directories, because for my case like all these different charge states needs to be hold in separate directories, it will be a long simulation. I would say like it will take a few minutes. So as you can see, that command actually created all these folders. So I have like for the interstitials I have like these 5 files, and for interstitials 2 I have 5 files for gallium. So all these things are created by that this command. Okay, so if you just run this this command, then it will work on properly. Then I need to copy my as.posker file to the posker file here. So as you can see, I have this as.posker file and I'm going to copy this to my perfect folder. So to do that, I can just run this command, and then you know, like if I want to see the defect entry.json file that is created in this process, I can just write it down, and here you will see that. So actually I think I need to run this defect entry.json file, because you can see here is no defect entry.json file. I think it should be under each folder. So if I just go here, and you might be able to see the defect entry.json file. Yeah, so it is under each folder. So if I just cd to any of this path and then write the command, you will see that all the defect entry things are already added. So for my case, as you can see, I have already like run the simulations for each of these directories. So how you can do that is that you go to the next command, and as you can see, if I just run this command, copy paste this and go to back to the defect folder and just clear these things a little bit. So what this command will do, that it will go to each of this directory, like it will have a for loop, go to each of this directory and then create VASP file. As you remember, like previously we also created some VASP because when you will create this defect directory, there will be only posker file and defect entry.json file, but when you will run this command, all the other 3 files like the incur file, then the posker file will be created here, incur file and the key points file will be created here, and also the podker file. Okay, so remember that in this case what will happen is like when you will run this command, BIS or PyDefect will automatically search the pseudopotential directory that you have already provided, and it will look for materials that are in this postcard file. So if you are like considering a file where there is silicon impurity, then you have like three types of materials. You have the gallium, you have the nitrogen, and then you have silicon. So what it will do that this command will automatically search the pseudopotential directory and will gather the pseudopotential of gallium, nitrogen, and silicon, and all together merge all together to create the podcast file for that specific folder that is for silicon impurity. Okay, so in this way, this will be automated process. You just need to give some this command. For my case, I am giving some personal command, like I am setting the energy cut of 520 NSW. This is the step size is 140, number of core use is 32, and energy difference minus 0.0.03. This is custom. You can do that in this way. And also I am using this command to make the BIS files for each of these directory. So I'm not going to run it because I have already done that. Okay, so then what you need to do that you need to run this command. So what this command will do, as you can see, it will once again go to each of these different directory, and it will just copy my Slurm package. This is my Supercell run that is under here. So if I go here, as you will see, this run package that actually holds much more higher computational requirement, like 256 gigs of RAM, 4 nodes, each have being 32 tasks per node. So I'm going to copy paste this Slurm package for all of these folders, because I need to run these folders, and for that I need the Slurm packages. And the third thing that I will do is that I will run this command. So once again I'm going to this folder, and here what I will do is that I will run it. I'll run, I think I have miscopied this. Yeah, sorry for that. So yeah, I need to run this command. So in this command, as you can see, I will go to each of this directory and then run my asbatch slurm file. So this asbatch run the slurm is actually where I submit my VASP job and then wait for the output. So when you run each of these three things one after another, then you will create this directory, then you will copy the Slurm packages in each of these directories. So this is for myself. If you are working on MPRN or anything else, you should copy paste your MPRN program in that folders. And then the third thing is that I'm running each of these VASP calculation for each of these folders. Okay, so this is what this calculation does. So after you have run and finished calculation for all of these things, then you will need to parse all the results from these defect induced directories. So one of the things that I want to tell you that you should remember that to set NSW, that is number of states, much more higher, because if I have tried like 100, 110, and it's still sometimes not all the impurity files are converged. So if you want to like have a converged result and a complete relaxation of all those things, then you need to make sure you have a higher NSW. So I would recommend you stick with the 140 and it will be okay. So after that, what you need to do, that you need to create some supercell parsing result. You need to parse the supercell calculation results. So to do that, you just copy this. So what it will do, that it will try to use VASP package to generate all these things, and when you run this all commands, it will create a calc results.json file. So let me just run it. Before that, I need to clear this. Okay, so let me just copy paste these commands for you. Okay, so after you have run this this whole thing, you will create calc result.json file, and let's see, and it will be generated in all these calculated directories. So if you go to one of these directory, and you will see that calc result.json file. So this will be created in each of these folders. Okay, well, I actually forgot to add a step, so I just updated my GitHub file. So after you first all this defect induced supercell calculation. Then you need to correct the defect formation energy. So we'll be using EFNV method. So if you want to know more about that, you can come here. This is where we are going to correct defect formation energy using extended FNV correction method. So for all you need to do that, you need to go to this, you need to use this whole command. So to do that, you can just copy this total thing and just paste it here in your directory. So if I just clear this a little bit, and if you run this, and it will automatically purge all the different calculations. After running that, you will see that in each of these folders in the defect, let me go to the defect, and in each of this folder there should be another file created called corrections.json file and corrections.pdf. So as you can see how this extended FNB method actually corrected your structure. So to know about more about this method, you can just come here and see this to paper for the reference. Okay, after doing that, then what we can do is that we can create this defect structure info. So that now that we have actually corrected our defect formation energy, we can just make the defect structure information. This is the final, like the most up-to-date information that we could use in our further calculations. So just copy this here and run these things from this defect folder. Okay, so this command will actually create, if I come here, step 12, so it will create like defect structure info.json file. So if I come here, you will see that this file, defect structure info.json file, will be created by this command. So if you want to like know about this more thing, just open the terminal and use the command PyDefect underscore print, then use defect entry structure info.json and hit enter. Finally, what we can do that we can actually copy this thing. So if you want to like see what is the crystal structure of this defected supercell, you can just run this command and it will create VASP file for each of these different types of defects. So if you just hit enter, and it will create VASP file. So if I go here, let it wait, finish a little bit, since I have already done the simulation. As you can see, defect.vesta, so this is for this file, and if you go to the next file, there will be another defect.vesta. So if you just open it using Vesta as a, if those who don't know, Vesta is like software for materials visualization, and it is very free. It is open and free to use for, okay, and it could be, you could use it in both Windows, Linux, and all those other tools, other operating systems. So yeah, so after that, all you need to do is go to step 13. So for step 13, this is an optional step, but I have already performed that, and I would suggest if you want to, you can do that. So all you need to do is just copy paste everything from the defect folder, and it will work just fine. And one of the things that I want to do is that I want to tell you is that when you come to this stage, and if you run this line, and if you fall, if you face any error, then do this, run this command. Okay, so this is the command that actually PyDefect provided us to follow in their this step, this section, optional section, but I was having some difficulty running it, so I tried this. So either you use a for loop, or you go to each of this directory, like each of this defect directory, you go to each of this defect directory and you just run this command from that directory. Okay, and hopefully that will work. Okay, so that being said, now you know, after this step, in each of your directory you will have some files. Let's just summarize. You will have the calc results file, you will have this correction file, you will have this defect structure file, you will have the VASP files. Okay, and finally we are ready to plot the defect formation energy. So to plot that, we need some information. If I come here also, you will see that we will be needing 3 files actually. One is from this calc result from the perfect folder. So if you come here, there will be a perfect folder, this is the perfect folder, and as you must know that the perfect folder holds the perfect structure with 150 gallium and 150 nitrogen atoms. There are no vacancy, no interstitials, no antisites, no impurities. So this is the perfect one. So we will be also considering this as the reference to compare all the other defected structure. Okay, so we need to give the information of this one, and also we need to give information about the basic unit cell that we have actually considered. So if you go back in our unit cell, this file has already been created in the previous step, so we need this file, and also we need the standard energy from the complementary phase diagram step. So to do that, if you have followed my video, you have already created sorry, not here, CPD. So this is the file that we will be requiring. So we'll extract all the different information to plot the defect formation energy. So when you will run this command, uh, uh, and it will like generate some files. So let's see what happens here. So if you just copy and paste it here, and it will try to extract all these different informations. Okay, and uh, this will create like defect energy info.yml file, and it will be created in each of these folders. So if I go to the defect folder and see, there will be another file, defect energy info.yml. So this is the file that is created by this step. So let me just revise this section. So I updated the file with this line. So as you can actually think that before the formation energy diagram plotting, we need the energy of that is relevant to each of these different types of defects, right? So that is why we need to run this code, and this line will create defect energy info.yml file in each of these defect directories. So if you go any of this defect directory, there will be this file, not this file, sorry, this file will be created there, defect energy info.yml file, and it will hold all the different information regarding this defect. So this is the defect where gallium is in interstitial position with charge stress 2. Okay, so uh, just follow this code, and then we need to create a defect energy summary.json file. So till now all the full different types of files are created in each of the defect directories. Now we need to extract all these different types of information from different types of defect directories to one single file. So whenever you will see these types of writing like in the parent directory or in the defect directory, what that means, let me just clarify that a little bit. So defect directories, when you will see this line or this part, it actually refers that in each of these directories. So this is a defect directory, this is a defect directory, this is defect directory. So the file will be created in each of these directory, and when you will see in the parent defect folder, that means that it will be created here, not within this folder but within this directory. So here you will find some file in addition to this file. Okay, so let's just run it and try to see what happens. Let me just clear this terminal. As you can see, I have actually done a lot of simulations before here. So as a result, I have majority of the files already created. So don't worry about that. It is just to make sure that when I am actually making the video, I don't have to wait a long time. Okay, so as you can see in the here, some files are created, like a defect energy summary. It's created just right now. As you can see from this time, it's 12:38, it's 12:37:59. So this file is created. So this file holds all the different information of all these different directories, and it is a summary of all those things. Okay, then you can run this command, and this will actually create a calc summary.json file. So we can also do that. So one thing that I want to show you, that in my case there are some failed directory. This is because I am just copy pasting some of the previous simulations here, but when you will be running this, you won't have any single issues. And if you ever see like any of this failed directory, you must check beforehand, like all these different step from step, like when you will be parsing the data from step 11, when you will be running these commands from step 11, if you ever see anything like the failed directory, make sure that you check it. And if there is any failed directory, you then it could be two things. There could be the condition that your VASP calculation is not converged. In that case, change the parameters and try to run again. Make sure that you don't have any failed directories. For my case, it's okay because it doesn't matter, because I have already copy pasting some of the previous data. But for your case, make sure that you don't have any failed directories. Okay, and some of this process will actually take some a few minutes to like 1 hour or half an hour, depending on your simulation or your computing power. So I'm just copy pasting majority of these things, so it is okay with me. But for your case, if it's taking a little bit longer, it's still fine. Okay, so let me just clear this a little bit. And the previous command actually created, so we are here, and we created calc summary.json file, and this is created where? In parent defect directory. So we'll find it here in this directory, defect directory. So let's just refresh it and look for calc summary.json file. So this is the file that is created just now, right now. Okay, and finally we can now make our formation energy diagram. To do that, this is the command. So you can either use this one or that one. So why? Let me just clarify a few things here. So as you can see, here are the level. This is like the which file I'm going to make the formation energy of, using which information, and these are like the plotting. So last, starting from -L, all these things are regarding how you are trying to plot. So this let me just clarify, this is like the level. I am trying to plot point A or point B. Now what that means, let me just show you. As you can remember beforehand, when I was doing the CPT calculation, I told you that you should remember that in the CPT diagram there are 2 points. Actually 3 points. One is like gallium nitrate, and it is normal. It's not gallium rich, it's not nitrogen rich, it's just normal condition. Then you have 2 condition, it is like A or B. And when you are talking about A, is gallium rich condition, and it's B, it's nitrogen rich condition. So when you will try to plot here in this where am I, in this command, this A means gallium rich condition and B means nitrogen rich condition. So when you are plotting this, you can just switch from A or B. Remember that anything other than A or B will not work, because this only works based on these CPD points. Because as you can see, when you are giving it CPD information, it actually holds this information that you have 2 points A or B, where one is gallium rich and one is nitrogen rich respectively, and you can just run those. Allow shallow is like if you want to allow shallow defects, and this Y means that Y-axis level is -2 to 2, so it's like the Y-axis limit. You cannot control the X-axis limit. Now if you want to know more about how you can control this information, there are a lot of things like I would say, see, if you see this suggestion part after this simulation, there are this some suggestion part, and there is some information like if you want to, when you are trying to plot the formation energy, you can just run this command and it will give you whole lot different types of information, like how you can customize your settings. And I have also showed some settings that you can use. And okay, so let's just run one of these defect formation energy diagram. You just need to paste it here and it will create the defect formation energy diagram for your case. Yeah, so all you need to go, we need to just refresh it. Now defect formation energy diagram will also be created in your parent defect folder. So just refresh it and you will see this nice plot. So as you can see, energy A, this refers to that energy is of A point is actually generated. If you want to also see the energy point B, you can also create it by this command. So if I refresh it again, you will see that yeah, energy B is also created. Okay, so let me just open this file. So as you can see, this is my energy of A. This is the formation energy diagram that is actually created by the command, and this is for the nitrogen rich condition for B point, and you can see the formation energy diagram. Now if you want to like learn how to read this formation energy diagram, you can just directly come here and open and try to download this file pptx, and at the later section of this file you will see some information about how you can read this file. Now one of the thing that we often do is that sometimes we try to actually create since we are using PBE, we sometimes also want to see the like what is the HSC diagram if we extend the band gap. Like my band gap is like only around 1.7 electrovolt for gallium nitride for this crystal structure. This is for PBE, but when you go try to like consider HSC, it's around 3.4 electrovolt. So if you want to like extend your PBE diagram for HSC, you can also do that. I have already done that. Let me just copy paste some of that information here. So if you just if you want to do the HSC extension of this like this kind of thing, where I have actually tried to, as you can see, increase the band gap from 1.7 to, so this is the band gap here showing it's the PBE line, but from 0 to 3.4 it's more like HSC. So I have just extended the band gap for the HSC limit. Now to do that, all you need to do is that you need to change some information, and those information you will find in your if you come here, the information actually are from this unitcell.yml file. So if you want to do the HSC limit, all you need to do is you change a hard code. You just manually change the band gap maximum, balance band maximum and conduction band minimum points in the unitcell.yml file. So what that means is that when we are before running this command, if you want to see the HSC limit, all you can do is that, let me just go to my unitcell.file and like okay, let me just make it copy and then create a new file. I am just sorry, let's call it unitcell hsc.yml. okay, and just add the information of the basic one to here. All you need to do is just change the balance band maximum and conduction band minimum. So in this case, as you can see, the band gap is like around what I can see around like to 1.8, around like that, 1.7. But if I want to like do it, extend it to like 3.4, what I will do that I will subtract 1.7 from 3.4, so there that will be like 1.7, and divide 1.7 by 2, so that will be like so that will be like around 0.85, I think. Okay, so what I will do that I will since balance band minima maxima, I will reduce this by 0.85, and I will increase my conduction band by 1.85. so I will increase 0.85 to this, and I will minus 0.85 from this, and as a result the balance band, the gap between balance band maximum and conduction band minimum will be increased. So after doing that, all I need to do is I will just change this line with unitcell underscore HSC to trigger it to this file, and then I will run every other steps. So in this case, what will happen is like the band gap will be created only for band gap will be the formation energy will be created based on the HSC band gap. So let's just copy paste it and try to do that. So I am going to do is just increase the HSC. So before that I need to change this file. So let's add 0.85 to this thing. Okay, if I minus 0.85 from here, balance band maximum, it will be around 4.38, and if I reduce it from conduction band if I increase it to conduction band minima, so 7.0786 plus 0.85 gives us around 7.9286. so yeah, so as you can see, the band gap is actually increased. It's increased much more, and it's towards the HSC limit. Just save it and now run these commands one after another. The rest will be okay. All we are doing is that we are hard coding the unitcell.yml file, and similarly also here you use unitcell.yml file instead of only unitcell. unit cell hsc.yml file. So in these two lines here and here, you just change the file name, or you can just, if you are using the same file name, then it will be okay. I would like always to make a separate file so that I am not changing my root file. Okay. Yeah, that is also done. As you can see, there is a warning that supercell conduction band minima is lower than the unit cell. It's okay, because for supercell we are not changing the band gap, we are just changing the band gap for the unit cell, because we want to see what would be the how it would look like when we will extend this band gap to the HSC limit. So after that, we can run these basic commands. Let's run this. Wait for a little bit for it to finish. Yeah, it's done. And finally, now we can run this again. This time, since whenever you will run this, it will create this file that is called energy A. So I'm just trying to make sure that it's not overwriting my previous file. So I'll say tell it as this PBA. So the new file, when it will generate, it will be not PBE, it will be HSC, or I will think it as an HSC, and it will not overwrite my file name. Okay, now I am ready to just run these two commands. Let's copy this and then paste these two commands. Okay, let's refresh this, and as you can see, two new file is created, energy A and energy B. If I open this, as you can see that yeah, the energy is extended. Now this is my band gap. So don't worry about this, like about the shape of this. There should be transition, and the actual plot is actually looks like this, more like when you extend this and to this HSC limit, it will be looking like this. So as I said, I am just copy pasting different directory for convenience, since I will be not running simulation in this tutorial, but I am showing you how you can do everything. So don't worry about that, just follow my technique to change the unit cell parameters from the unit cell.yml file, and you can extend your PB output to HSC limit. So I think that is pretty much it. So some few other things that I want to mention. So there are some other things here, like how you can get help in PyDefect. Also some random stuffs, like if you want to see bus, if you want to create a bus run sh file for a folder that has a lot of folder within it, you can do that. You can use these commands, you can check it. These are all shell script. And also if you want to know how you can add new line or sorry, add remove new line or remove a line from your any file, like the incr file, you can just follow this. This is how it works. You just run this with your own file and try to see how it works. So this is pretty much it. So here is the final 2 cents. If you are trying to run it from the very beginning level, I will suggest you follow my GitHub repository, but still I will also suggest that you follow their official website. So if I were you, what I will do is I will read their steps and I will try to run the commands from here. So because I have the commands here that are pretty much comprehensive, you just need to run this and it will work. But to know what is going on, I would suggest that you also see this, because it will help you to know much more about the codes, because there are a lot of codes that are used in their small detection, like when you are using like bus PyDefect bus, then it's MP. If you don't know what that MP means, then I think you should know it. Or whenever you are working with BIAS, then BS, what that BS means, you can all get all this information from here. So just read it and try to run it here and try to follow all these steps, and hopefully you won't get any trouble. And if you ever feel any trouble or if you ever face any issues, then just comment and I'll try to reach out. And if you like this tutorial and have any feedback, please comment. And also I would suggest if you share it with the people that you know of. So this is part of my PhD research work here, and I'm trying to trying to show you all these things so that whenever you will be working on that PyDefect and VASP and defect calculation, you can have a reference to work to get start your work. So thank you very much for being with me during this whole tutorials, and I will come with some other information or other playlist hopefully. Till then, goodbye.